Hey, well, thanks for being here tonight. Welcome to May. Um, we made sure that we're following the Gregorian calendar, so we got to May now. But I appreciate everybody's time tonight, support, and I really appreciate Geoff Mathews for agreeing to talk to us tonight. I met Geoff at the SVAS presentations that happened at Foothill College, and and frankly, he was a willing ear, and I asked if he'd come and talk to us, and he happily said yes. So I really do appreciate you being here for us tonight, Geoff. Um, just as an introduction, Geoff is a full-time astronomy professor at Foothill College in Los Altos. There he teaches general education astronomy, lecture, and lab courses. And a few years ago, in response to the deprecation of Flash, making hundreds of browser sims unavailable overnight, he founded the Foothill AstroSims project, which develops astronomy education simulations that scaffold student learning and ours um, on topics that they would otherwise not be able to address mathematically or visually. He's also involved in the Lick Observatory Astral Project, which provides Bay Area Community College and CSUs with access to the Mount Hamilton Observatory. And the topic tonight, and it's here on the screen, and I won't read through all of it, but really, Geoff, I know you're going to launch into the explanation of really how we can learn based on simulations and the information that's available online to get us to a point where using our computers, tablets, phones, other equipment, we can actually do a learn more about the universe and simulate activities in the universe. So again, Geoff, I want to thank you, and I'm going to turn it over to you. And we've got about an hour or however long you need, and we'll close with some Q&A. So,
Okay,
yep, and thank
great.
you.
Thank you so much. Oh, and as much time as I need. Okay, so 5 hours later. No, but also, just something funny. I realized the photograph that I sent you. This must be my favorite astronomy shirt. So, so at any rate, yeah, let's go ahead and get started. Thank you again for the invitation to zoom in and speak. Sorry, sorry I'm not there in person, but it's quite a long drive for me. So, yeah, so I'll be talking about astronomy education simulations and giving kind of a broad overview of the topic. And trying to give you a map, so that way if you decide to dig further into the topic, you've got a little bit of a guide, a little bit of direction to where to go with this. So a little bit about me. Um, back in my research days, I studied circumstellar disks, the leftover material of star formation that went into building planets. And it turns out, though, that that research experience is not what I'm drawing on now. I'm actually building on experiences that I had as an undergraduate. So when I was an undergraduate physics major, I was actually involved in education research. And so I was involved in a project back then called participatory simulations. And the idea was that we focused on phenomena where you would have many interacting parts, each following their own particular rules. And out of the interactions of those parts, you would get a different emergent phenomena. Now, that was actually sort of so that's the concept is emergent phenomena. So an example of this is we would take students, give them motion detectors, have them bounce around like atoms in a gas, collect their speed information and histogram it. And so they had this personal experience that they could then use to think about, even just interpreting a histogram. So because for many of the students that we worked with, it was their first time seeing a histogram, discussing why was it that, they had a few times somebody measured at a high speed, oh, that's Johnny racing across the room. Why did they have a lot of the times a measurement of people moving at low speeds? They're like, yeah, we don't want to bump into each other hard. But then using that as a jumping off point to say, study the behavior of an actual gas, which we could then have computer simulations for them to investigate. And so that experience as an undergraduate, my involvement in that research project, is something that really stuck with me. And when I taught for a while. I was a high school physics and chemistry teacher for a while. And then when I left and went into astronomy research, this was always floating around in the back of my head. So that when I then started teaching astronomy, it was kind of these use of simulations became just part of what I did. It's kind of part of the air that I breathe as a teacher. And so when it comes to teaching astronomy, there's a wide range of simulations of astronomy topics that can be used for teaching. And here I just have kind of a, a screen, tossing a bunch of these out at you in terms of little animations. But we'll end up talking about sort of all of these that I have up here in a minute. Let's actually kind of take a step back. Why? Why are we even talking about some tool for teaching, right? We got textbooks, we got pencil, we got paper. Well, when we think about how learning happens, here I've kind of put up on the screen kind of a schematic of the big picture components of how learning happens. Learning really is just the process of thinking and revising your thinking. Well, if you're going to revise your thinking, you're going to need feedback on your thinking. If you're going to get feedback on your thinking, you need to be exposing your thinking somehow. When we're scientists making discovery, the way that we're getting feedback on our thinking is by coming up with experiments, by saying, oh, let's go observe this or let's go observe that. Let's get our feedback from nature. But in a classroom, we don't necessarily have the time or the equipment to get our feedback from nature, right? If you're wanting to figure out the orbital period of Saturn, you're not going to sign up for a class that goes for 30 years to give you the chance to make that measurement yourself. So what ends up happening in classrooms is we're getting our feedback in other ways. So we're sharing our thinking with our classmates, perhaps in a discussion, or sharing our thinking with our teacher through an in-class poll where a teacher might ask people, which of these is the next thing that'll happen? A, B, C, D, and having people hold up fingers, or the homework, right? You turn in your homework and your teacher gives it back to you, with lots of red ink on it. But those ways of getting feedback are um, often they take a lot of time, right? So thinking of homework, right? You might turn in your homework on a Thursday and it's Monday or Tuesday before you're getting it back. And of course, the whole time you were working on that homework, you might have had some misconception. So if you were working on that homework for a week, maybe it's 2 weeks that you have this incorrect idea in mind and you're not getting feedback on it. But feedback is what we do to revise what we need to revise our thinking. And so when I talk about simulations in astronomy education, I'm talking about a tool that can really tighten that feedback loop. So, for example, um, I might in a class throw up a picture like this and have a discussion with students, right? I'm getting people thinking and getting feedback on their thinking. But that's a situation where sort of the feedback is still coming from me as the instructor. I'm being the arbiter of, is that right or wrong? But I could give students a tool to let them actually kind of act upon their thinking. They might look at this and say, well, using my hands and waving them around, I think that this is a couple of galaxies that are colliding like this, or maybe like this. Well, we can give a student a simulation where they can actually set up a couple of galaxies right there in the class, right there on their phone, and they can hit go. and they can check for themselves. Did I come up with a situation that matches what we're actually seeing? And so by giving students a tool that allows them to, in essence, play with the universe to say, what does it look like if you've got a couple of galaxies hitting like this, or like this, or like this? What would that look like to us on Earth? By putting those tools in their hands, they can go through a process that looks a lot more like doing science and a lot less like saying something and checking with the teacher to see if it's right. The use of simulations in teaching, not new. In fact, I forgot to throw on my slide here. Chess was being used to teach soldiers the art of war 1500 years ago. Um, and in a sense, every time you write out a mathematical function or a differential equation, that's a simulation, right? You can work through all of the math for a bridge before you've set down a single brick. Um, but sort of zooming to things that are more clearly kind of simulation and stepping away from kind of the formal mathematics skills, getting into things that are closer to my topic for today. They're one of the earliest examples that I've been able to find was, for example, the beer game, which was used at MIT's business school for decades. Day one, every MBA student would be sat down at a table, given a different role in a distribution system, and then they got to watch it crash and burn. And hey, that's a good motivation then to go on and pay attention in those business school, those logistics classes. Or within astronomy, people were doing things where they were having students act out motions, right? Act out viewing things from here or there. That's a simulation. When you hold out a tennis ball and walk in a circle around it to be like, well, what if I'm the Earth and that's the sun? You are simulating that system. With the propagation of inexpensive electronics starting around in the 80s, people were developing computer programming languages for students to be simulating physical situations. So, for example, here's an example from a language called NetLogo, which is designed for students to be able to on-ramp quickly to using of gas in a box, right? And very quickly we see that the you end up with particles moving at a range of speeds, a few of them really fast, a few of them really slow, a lot of them in the middle, just from a few simple rules concerning what happens when two particles collide. About a couple decades ago, we started to have um, browser-based tools. And these opened up new availability for simulations to students where, no longer did you need to install software on a computer, right? Which is a real hurdle for a lot of people. But you could just click on a link, go to a web page, and all of a sudden you can be seeing acting out the old Earth-centered model of the motion of planets. And furthermore, you could actually go in and make adjustments to see, oh, what if that motion around the Earth was slower? Or what if that second little loop was slower? Now, simulations like this, the benefits that they bring to education, there's a lot of benefits, but out of all the research that people have done into the topic, and that research goes back decades, um, they're simpler than real life. And that's a real advantage. Um, if you think about scientific progress, right? Why did it take so long for humanity to figure out basic physics? It's because we live in an environment with friction and air resistance, right? How difficult is it to figure out Newtonian mechanics when you constantly have you constantly have situations with multiple forces at work? And so being able to simplify things can make it easier for people to start building up those pieces. You can experiment with things that you can't manipulate in the real world, right? You can do that what if reasoning. Um, Thinking of orbits, right? We can't just make the sun twice as massive and see what happens. Ooh, let me put that back. Um, so, we can't just change things in the universe, but in a simulation, we can. And so we can do what if reasoning that's otherwise impossible. Simulations can also be tailored to emphasize particular goals in our teaching. Another huge advantage, and this is particularly valuable for astronomy simulations, is being able to present multiple views of things at the same time. Being able to for developing an understanding of the phases of the moon, there's a lot of value to being able to simultaneously see, here's what I would be seeing from the surface of the Earth, and here's a top-down view of the Earth, Sun, Moon system. They can also be used to support analysis in situations that would be beyond students' sort of formal mathematical skill set. Thinking back to the project I was on as an undergraduate, um, one of the topics one of the participatory simulations that that we worked with students with was disease propagation. And we had fourth graders developing within minutes calculus concepts about rates of change and the relation between, the fraction of the populace that's sick, the fraction that's healthy, and the rate at which people are getting infected. That was just magical. Seeing how far the students were able to go beyond their formal mathematical skill sets, doing conceptual reasoning supported with these tools. And another huge advantage that they bring is agency in general is a major part of engagement, of maintaining motivation. And so, with a lot of teaching, students don't feel agency, right? They're okay, they're just being told the next thing, being told the next thing. But with these simulations, you can put them in somebody's hand and they can be given room to experiment. Be like, you can give them challenges. With one of the simulations I'll show you in a bit, looking at orbits, I just tell my students, find as many ways as you can to destroy the Earth. And that sort of, challenge, people really find engaging. It helps get people, turning on their brains, right? Because if you're not engaging with things, if you're not motivated, right, that sort of upper left corner of my schematic here, um, you're not going to think. And so simulations that I'll be talking about, the thing that they're doing is they're allowing us to take our learning cycle that's happening in a classroom, where we still have all of these other things going on. We still have the discussions, we still have polls, we still have, students working together or working individually, but we're also, when we're giving them these tools, giving them a way to not have to be checking with somebody else. They can treat the simulations as a model of nature. We can say, trust this to give you an accurate or an accurate enough representation of reality. And now you check your thinking. But I really want to emphasize a last key point. Yes, these can tighten the feedback loop of learning by, if somebody has a simulation, they can check their thinking, right then and there. In a world where they don't have these tools, they're having to wait to hear back from me. If somebody sends me an email at 11 at night, I'm not getting back to them at 11:15. Um, but if somebody has a tool that they can use, they can check themselves right then and there, but they're not a panacea. So something I really, really want to emphasize is that these are still just one more tool to be putting on our teaching tool belt. Whew, that's a lot of preamble, isn't it? Now, the landscape of browser-based simulations. So at this point, I've cataloged more than 300 um, of these tools that various people have made out on the internet. Dozens of people. There are a few big projects, like the University of Nebraska-Lincoln had a big project that went for years. PhET, the University of Colorado, has a big project still ongoing. Um, there have been other smaller projects of one or two people where, they've produced a dozen or a few dozen simulations. And then there's just oodles of simulations out there where somebody was just interested in this one topic. They made this one thing, they've put it up on the web, and it's just out there for people to use. So kind of a little archipelago of one-off simulations. There's a lot of simulations that focus on mechanisms where you can actually change the rules of the universe or change the number of objects in a situation or change the orientation of things in a situation. There's also simulations that focus on just the observation side of it. This is a huge thing for astronomy. So much of the challenge of astronomy comes from how do we use our view where we are stuck here on the surface of a planet? How can we use our view from here to figure out big picture arrangements of things? And so observation simulations play a really big role in the space of astronomy education simulations. And then there are also simulations, they're kind of edging out of the simulation range and more kind of showing comparisons of data to models. So it's, there's a lot of kind of fuzzy lines. What is a simulation? What's not? And so let me show you some examples of these things, right? Because I'm talking about these, I'm giving out these terms, but what do these actually mean? So one example of a mechanism-focused simulation would be uh, the spectrum constructor that I made to help me with teaching my classes, where in a typical class, when I first started teaching astronomy, and I'm trying to get people to understand spectra, I would have one day right at the start of the quarter where I'd bring in emission lamps and I'd have everybody with their diffraction gratings. And so I would show people these things one day. And then I'm counting on that lesson sinking in that one day to be using all the rest of the quarter for people to be looking at spectra like what I have down at the bottom. A line showing at this wavelength it's this bright, at this wavelength it's this bright, at this wavelength it's this bright, and reasoning backwards to what would that look like, how to interpret this. Well, it's really handy to put in somebody's hands a tool where they can just make whatever spectrum they're trying to investigate. Oh, I'm looking at an object that's glowing because it's hot, like a star. Okay, I'm going to make a thermal spectrum. I'm going to adjust the temperature. And then they have a view of just what would that look like by eye. So if something is 4,500 Kelvin and you're looking at it by eye, it's going to look kind of yellowish. Oh, what if it has some helium glowing? Oh, if you look at it with a diffraction grating, you're going to spot a few colors showing up brighter than others. What if you have your spectrometer and you will actually be able to measure, oh, it's getting, as we're going from short to long wavelength, it's getting brighter and brighter and brighter, and at a few specific wavelengths, spikes in brightness. And this is a tool that students can go back to and they can keep using throughout the course whenever they need a reminder of these concepts. Or, as they're working on a homework and they see a spectrum, they're just like, wait, what does this mean again? They can, I'm having to interpret this thing. They can go back to this tool to help themselves out with it. But the mechanism here is that they can actually play around with an object and say, what if it is glowing in different ways? Or one of my students a few years ago built a dark matter simulator where here we've got a bunch of dots orbiting around. This is showing a schematic view looking down on a galaxy, looking down on a disk galaxy. We've got some stars near the middle that are orbiting quickly. We've got stars way out on the outer edge that are moving slowly. But the key thing here is you can actually change it. You can change the physical situation. These little sliders along the top there that my mouse was going over and adjusting. So we can actually letting us actually change the concentration of dark matter in different locations in the galaxy. Now, normally we can't see dark matter, but in the simulation we can. We can just have our little checkbox to say, yes, let's see the dark matter. Let's show it in shades of red. And furthermore, we can use this to actually figure out the dark matter distribution in actual galaxies. So in the middle on the right here, we have a graph showing the actual measured orbital speeds of stars in our Milky Way galaxy. And so, the video is showing going through and adjusting the amount of dark matter until our model orbital speeds are matching up with the observed orbital speeds. We're able to use this to actually learn something real about our galaxy. In this case, if we find our location in the Milky Way about 25,000 light years out from the middle, we can see that within every volume, within every space, the volume of the Earth, there's about half a kilogram of dark matter. So that's about one squirrel. So if you noticed that XKCD comic last yearish sometime. Or you can play around with the physical situation by saying, hey, let's have a distant galaxy. Let's put a galaxy cluster between it and us. Let's adjust the mass of that cluster in the middle and actually see how it changes the lensing that we see, which is shown, so here we have a situation of seeing a top-down schematic view of a distant galaxy, a cluster, us, and light going from that distant galaxy to us. And then the view at the bottom showing, hey, we actually see that distant galaxy a couple of times, off to the left and off to the right, because the light has been bent around. And I mean, examples of this just go on and on and on. You can play around with the mass of a planet orbiting a star, and how would that end up changing what we would see with our measurements of the Doppler shift of the star? How would that change if it's oriented just edge on to us? How would that change our ability to see little dips in brightness of that star as the planet's passing in front of us? So hundreds of these simulations allowing students to reach in themselves and change the universe and do that what if reasoning that was really powerful for learning. So those are examples of mechanism focused simulations. Then there are simulations that are really just focusing on observations, being able to act out viewing things at different times. So, for example, a tool called Stellarium, which lets you pick any time, pick any location on Earth, face off, point yourself towards whatever direction you want to point on the sky and be able to say, hey, what would we see at that time? And so this is a tool that I use a lot in my lab classes because I want students to reason about, how do we know the orbital periods of the planets? Well, I think I made the offhand comment earlier about not sticking around for 30 years to figure out the orbit of Saturn. Well, with a tool like this, we can. So, we can study the motion of Jupiter not necessarily by going out night after night after night and looking up at the sky, a task which, you know, we tend to underestimate sort of how much skill goes into just going out and looking. Um, it's not the kind of task where you can tell students, hey, go out and look, because you're just going to get back gibberish from most people in terms of because they just aren't trained to see. If you have a lab class that's at night, then you can do that training and set people loose to do this. But if the schedule doesn't work out for that, if like if my labs are scheduled during the day, then a tool like this lets you pretend to go out and see, lets you see what would we see if we went out night after night. Or being able to, see things from multiple perspectives, seeing a top-down view of the sun and the earth and the moon simultaneous to the view of the moon, being able to see, think through. what would be this be looking like from different locations? You can use this to kind of check that you're developing the underlying skill. Because if somebody really understands why we see the moon phases we see, they're also going to be able to figure out before they check what it would look like for the moon or what it would look like from other places in the sky. So a tool like this can be used to both build up the understanding. Let's see what the moon looks like from Earth, hit go, but then to also extend their understanding. And then there's that last class of model overlays on data, where this is a smaller number of people doing work like this, but situations, for example, where you say, here we've got a spectrum, let's figure out what type of galaxy it is. So the blue line there is showing a measured spectrum of a galaxy. The green is saying, here's models of different types of galaxies. You can then adjust your redshift to see, hey, when do we have a match? And so allowing students to go through that same kind of process that scientists go with the data that we collect, or being able to explore, for example, when a new asteroid is discovered before we've really pinned down its orbit, being able to say, hey, what are the possible futures for this thing? Which you can then use, over time, the next night you can be bringing in the additional data from the next night and see how that's narrowing down. So I could go on and on and on. This is why I kind of joked earlier about like 5 hours later, right? Because, oh, 400 some odd of these things that I have found, right? And that's just what I found. I've kind of set myself the task of finding and curating the browser-based simulations that are out there. There and also categorizing them. And that's a big thing. So I've taken the list of what I found. This all started with just trying to find replacements for those simulations that were done by the University of Nebraska and Lincoln um, decade ago, because they had all been done in Flash. And 5, 6 years ago, Flash became deprecated. And so I started on a quest of finding replacements for these tools that I'd been using in my teaching. Um, and then I realized, oh, there's a whole lot of others of these, plus the ones I've written. And so, I started listing all of these and have that out there for anybody to view. And you pick a topic, there's probably a sim about it. So whatever you are curious about, somebody has written something to help you understand it. So when it comes to using simulations in teaching, so I've shown you some example simulations. Um, you know, they're a tool like any other in our teaching. Every tool has its its utility, right? A book is a useful way for students to have access to information at any time in any place. A pencil and paper is a useful tool for getting students to expose their thoughts, to share their thoughts with you. And simulations, they also are a tool that have their use. One of my favorites is with the gravitational, with the PhET project's gravity and orbit simulation. I challenge my students to destroy the Earth. And so, uh-oh, we have the Earth moving too quickly. Off it goes into the deeps of space. Or, we could then also use it after students have had that time of playing around with it, right? They're just trying the situations. We could then use it as a prop for discussion, right? Where we say, hey, share what you did. Somebody says, oh, I try, what's going on here? And students can share their ideas. They could say, oh, well, we think that, gravity is having this effect, the motion of it is having this effect. oh, it seems like when we're moving the planet further away, the gravity's getting weaker. We move closer, it's getting stronger. And so we can have this live, free-flowing discussion, figuring out the rules of the universe together because we have this way to kind of play with those rules right on the spot. Another use for these simulations is something that can be embedded as part of student preparation in class. So, for example, I wrote a simulation a couple years ago that uh, acts out the lifespan of a star. Now, it's greatly simplified, right? Really just saying how, mass, that's how much fuel you have, luminosity, that's how quickly you're using your fuel, not taking into account any of kind of the details of the changes that go on in the core over time and how that's changing the lumen. Way too much detail, right? We're focusing on just the big picture concept here. So this goes back to what I was saying earlier about one of the advantages that we can simplify things, right? Let's focus on the biggest picture view of what's happening so that people have, a baseline that they can then add those further details onto. And so as part of students reading, I can have, here's a few paragraphs that students have read, and now actually play around with it, right? So I can say, try and see for yourself before coming into class. What is the effect of mass? What is the effect of luminosity? Wow, that high luminosity star just out of fuel like that. What about realistic stars? If a star has a really low mass, is it going to have a high luminosity? No. Your high mass stars, though, will. And this gives students a chance to play around with the mechanism, right? Mass, that's how much fuel you have. Luminosity, that's how quickly you're using your fuel. To understand how, with real stars, those factors combine together to cause our low mass stars to have very long lifespans, our high mass stars to have very short lifespans. Before I had this tool with my classes, basically almost everybody was limited to just memorizing. High mass stars have short lives, low mass stars have long lives. Because a lot of the students coming in, particularly for, our gen ed classes, you know, those formal mathematical skills, that comfort with mathematics isn't there. And so this is allowing them to do reasoning. This is supporting them in doing reasoning that they can do beyond what sort of their formal mathematical skills support. Another use, which I kind of alluded to earlier, is having students act out observing. So you can say, hey, let's go to a particular date and time. What do we see on the sky? Let's advance the time. What do we see happening from day to day to day? Simulations can also be used as interpretation tools. So you might have data. So here's an example tool that somebody made that actually, gives a very nice interface for the Sloan data set, which was a big survey that measured the brightness of a bunch of stars in a couple of different filters, and along with that measured spectra of a bunch of stars. So they made this great tool that lets you look at stars, you know, all these different combinations of color and brightness. So colors, being our temperature, being able to click on them to see, hey, what's the spectrum like for that? Well, then you can load up that spectrum constructor and you can actually make adjustments. Be like, hey, can I match some of the features that I see in that spectrum and use those matches to make some inferences about these astronomical objects? Hey, those dips in brightness are matching up with the dips in brightness caused by hydrogen. Hmm. It gives students a chance to to work with data to a level way beyond um, what would have been achievable. And you can also use them to segue from, here's a simulation where you can create a galaxy with a of a different size, and you see the globular clusters spread out throughout the galaxy. You can view it from Earth, right? So the center of the graph there is us, because this is our view from Earth. How far are things from us? In what direction do we look to see them? But you can also switch to a top-down view. And so these can support students in learning how to go through this process of saying, what do we see from here on Earth? Here's this way that we're representing those observations. And now, how can we interpret those observations to figure out the size of our galaxy, to figure out how far we are from the center of our galaxy? Yet another thing that we can do with these, and this is kind of a rarity so far, but something that people are starting to do more and more, is actually writing these tools with kind of built-in walkthrough lessons. So further streamlining the learning process where you can have your simulation. For example, this one from University of Nebraska on the left, visualizing the apparent speed velocities of galaxies, on a cosmological scale being carried away by the stretching of space, but then also having pop-up questions right there to help guide people through. I think about my own classes where quite often I'm writing a set of questions and then having the sim embedded. Um, and how many people do I lose because they're having to pop back up here, find the next item to read, go back down. And so anything that can kind of streamline that process for people is going to be a win. So I've, I've given you this whirlwind tour of some of these browser-based simulations and their uses. And um, part of the reason that I'm interested in browser-based tools is that ease of use. So um, early on in the early on in the pandemic, when I sort of instantly went online with my classes, I had been using a set of laptops in my lab class with the computer installed version of Stellarium. And at that time, the browser-based version, um, actually, I don't think I was even aware of it, right? And that switch and having to support people in installing Stellarium on their computers when it was a piece of software that was sort of not in any of the walled gardens that are used because it's code being written by astronomers. We don't have the resources to jump through all the hoops of getting into the app store, things like that. It was wow. But with browsers, you just click on a link. With browser-based tools, you just click on a link. And so that's that's been a very revolutionary component, a revolutionary moment, I think, in the use of simulations in teaching was when, a couple of decades ago when people started figuring out how to put these things in web browsers. Of course, the field has to keep moving on, and a big looming issue is accessibility. And so there's now a federal mandate that basically anything that somebody's using for teaching that is online has to meet a set of guidelines for accessibility. And with images, that's relatively easy. You can just write some alt text to pop up with it. With videos, you can have closed captioning along with it. But simulations, it's a really, really hard problem. Um, and I'm not going to get into all of the challenges there, but this is something where now the simulation community is really kind of kicking up an effort to to look into this and try to address this. Um, there's also maintenance, right? Tools. if a lot of these tools are the products of somebody having a little bit of grant funding, so they, you know, build a tool, but then, the grant runs out 5 years later, the people stop doing updates, and things just evaporate, right? There was a set of tools called Clea that was a really full-featured suite of observatory simulations where you could really simulate, like, I'm going to have a telescope of this size, this kind of detector, going to go looking off in this part of the sky. What if I had a bigger telescope? What if I had a smaller telescope? Change my integration time. And it evaporated. It was built a couple decades ago, worked on like Windows 7. Project didn't have funding to continue doing updates, and it's gone. That galaxy collision simulation that I showed earlier is a re-implementation of one that was done a couple decades ago in Java. And then, of course, when, Java stopped working so well in browsers, it evaporated. And so maintenance is a big issue. And and there's a lot of these projects, it's one person. I think of, my work at Foothill with my AstroSims, it's me. So um, so deprecation, which I mentioned, for a while, the Nebraska Sims, there's 100 simulations that were done at the University of Nebraska. And when Flash deprecated, they just vanished. Now, pretty quickly, people came up with a wrapper. There's a software called Ruffle that you can just sort of use as a wrapper, but that's just kind of a temporary fix. And that got them back to us. But there's also link rot. There was this great game, actually. So it was a simulation, but it was also a gamified simulation of triggered star formation that was made to accompany an article in Discover magazine. It was a really great way of exploring, how supernovas could push gas around and pack enough gas together. You get more stars, you get more supernovas. It's gone from the world. And, you know, people will put links, will submit these things to the Wayback Machine, but they don't always work. The star formation game, there's a link in the Wayback Machine, but it doesn't work. Fortunately, um, effort is now underway. The American Astronomical Society's Education Committee is kicking up an effort. We've actually just started this week. We had our first meeting yesterday, the day before, to start trying to organize our efforts, the community's efforts to preserve these tools. And of course, now thinking about it, it's like, oh, this is a lot of work that we're signing ourselves up for. But these have been very valuable tools for, when I think about tools like my dark matter simulator, the gravitational lensing simulator, these are topics which until now, or until a few years ago when my students made these simulations, um, these were topics that you could kind of address in a hand wavy way in a general education astronomy class, but actually doing anything with them, actually really getting in and thinking about them and trying out those ideas yourself, people just didn't have the formal mathematical skills for it until, junior year physics major or junior year astro major. Or for some things, I've been making a set of simulations to address the cosmological redshift. That's graduate level, right, in terms of the mathematics skills. But you can put these tools in people's hands to start reasoning about and thinking about these things um, well before they're hitting those mathematical skill levels that were formerly necessary, at least for people to develop an understanding and to have the experience of thinking about and reasoning about these things. All right, so I think with that, I'm going to go ahead and wrap up. I'll leave this slide up here in case any of you are interested in trying to find a way to help out the community of AstroSim users, and I'll go ahead and take questions. And I'll just slide that over here so that y'all can keep seeing that.
You know what? I'll kick us off with a question. We'll take others from the room, but you know, um, I look at some of the work that we do. We do a lot of outreach with schools and with the public environment. And I'm wondering if you have any simulations that you see as ones that you kind of your touchstone ones that you're using to engage the public arena. Because those are the kinds of things that I love to look at and see how I can actually help students and grow interest in astronomy.
Oh, yeah. So um, everybody asks about dark matter is one of the things that people ask about. And so being able to just stand with a group of people, pull up this thing, right? And being able to just to play with people with it. You know, you start off say, okay, you know, what's here I can actually show you where the dark matter is. Let's what effect is it having? What if we got rid of all of it? What would happen? Right? And it's not, the physics is not complete, right? Because actually, if everything stopped orbiting, it would all just fall together, right? So it's an incomplete simulation of reality, but it captures the gist. And so then being able to play with people, well, hey, what if we had a little bit more? What would that look like? Well, now here, this is showing you how fast things are actually moving at this part of the Milky Way. Do we have things moving fast enough? And then, and you have people, kids chiming in, oh no, it's way too slow, right? Our speed is down here. We're looking for a speed like this. Oh, well, can we get a match? Right? And talking through this with people, it really takes something that's a mystery because people be like, oh, it's mysterious dark matter. How do you even know it's there? And you can say, because, our galaxy looks like this. It looks like there's a bunch of stuff in the middle and not very much stuff further out. And if that's the case, this is what the orbits would look like. But our orbits actually look like this. Let's figure out how much matter is actually there using the orbits that we see. And you can have that conversation with people to really demystify this topic. And you can then start playing with it, where you can say, oh, okay, let's just not have anything. Let's hide our dark matter, right? And of course, you might have to put something over this side to hide it from people's view, but you could kind of play the game. You could make an arrangement and be like, hey, where's the dark matter? You know, throw up something to cover this part of the screen where they're just seeing the motions. And, people can then do this working backwards to be like, well, hey, I see stuff moving quickly here, moving slower here. That's giving me clues to where the dark matter's at. You can start to gamify it a bit with people.
Great.
Other ones, man, there's an overwhelming number, really just depending on people's interests, right? Like there's a nice simulation that some folks made, looking at, what are the paths for going from Earth to Mars? Well, okay, what if Earth is here and Mars is here in its orbit and we launch? Uh-oh, what's our problem? We didn't launch fast enough. Okay, let's reset. And you can you just play with it. What if we are going around like this? Oh, we launched too fast. Oh no, we're lost in space. And any of the Sims, whatever the topic people are interested in fact, you could do this. Just walk into a crowd, be like, what's something you're interested in? Okay. You then scroll down, find it, pull up the Sim, and just start playing with the Sim with them.
Yep, great. Thank you. Let me open questions here in the room. Oh, go ahead, Casey. Oh,
Hi, Geoff. My question is, your students, I'm sure they're enjoying that and they're getting the concepts and everything, but how does that translate when they need to apply it in the classroom, physically in testing or something, or actually being able to understand it?
So a lot of my design, so for example, my globular cluster sim. So this is starting off showing view from Earth, looking towards the center of the galaxy. The dots are showing globular clusters. So we look over there, we see a globular cluster. We look over there, we see a globular cluster. We look down there, we see a globular cluster. But then you can view from other places. You can say, oh, what if we are viewing this situation top down? So we so this is a tool that's letting people transition between our view from Earth, where we're looking out at a galaxy. We're looking a little bit to the left and we're looking a little bit up. Okay, we see a globular cluster 24,000 light years away. We look over here, we're seeing a globular cluster 25,000 light years away. See this one 28,000 light years away. So they can go through that experience of making that map. Because this is the type of thing that we analyze to figure out the size of our Milky Way. This is what we analyze. We look at globular clusters, we measure the distance to them, and we go to a radar map like this. We're at the center. So we were looking over here and we saw something, we were looking off in this direction, and we saw something 15,000 light years away. We also saw something 25,000 light years away, and we saw something 35,000 light years away. So each dot, 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 dot representing those. And that's how we then figure out, oh, the globular clusters, those are spread throughout our galaxy. So that's telling us that our galaxy is about this big. Is my cursor showing up as I'm moving it around, by the way? Okay. So
Yes.
that's telling us that our galaxy is about that big. And the center of that circle is around here. So that's telling us that the center of our galaxy is over there and not where we are at here. And then with the simulation, you can actually change it. You can say, well, hey, what if they're further away? What if they're close? What if the center is closer? And so that builds up the skill, because this is on my exam. I hand students a map of globular clusters of an, a fake galaxy. I say, imagine that we live in this other galaxy. Where is our home? Near the center, near the middle, near the edge. And so a lot of the simulations I make have been driven by, students are having a hard time with this concept. Let me build something to address that, right? My spectrum constructor is entirely a result of, students having trouble interpreting spectra, right? Being like, okay, the peak of the spectrum is over here, or the peak of the spectrum is over here. What is that telling us about temperature? Because they can actually play with it and say, okay, I'm going to make it hotter. Oh, my whole spectrum shifted off to the left. The peak is at a shorter wavelength. I made it cooler. Oh, the peak shifted off to the right. It's at a longer wavelength. So they're able to review those concepts themselves. They're not having to answer a question, wait for feedback from me.
Great. Thank you.
Excellent presentation. Thank you very much. My question is, do you see a place where the AstroSims blend with live behind the eyepiece nighttime astronomy in the field? And how would you see that as enhancing a student's education?
So some of the Sims, um, there there are some. So for example, I could imagine a Sim, one that's on my to-do list. So it doesn't exist yet, is a simulation where you can adjust the physical properties of two stars. Adjust the temperature, adjust the size. So, okay, how is that changing the luminosities? And then adjust the distances from us. So one side you have a top-down view where you're moving it closer, moving it further away. It's representing, the luminosity change, the size change, the color change. So you're having that top-down view of them. But then over here, that simultaneous view, what would it look like from Earth? Because this is one of those challenge points, one of those trouble points that my students have is you look up at the sky, you see two stars that look the same brightness, but are they actually the same brightness, or is one of them dim and close and the other one bright and far away? And so that kind of thing, that could be a tool, when you're teaching, you know, thinking back to when at my previous institution, we had labs that were specifically at the night, in the nighttime, so that we could take students out with telescopes and have them doing eyeball observing projects. And this kind of reasoning is one of the things for people to be developing. And it's hard, it's a challenging one. And so a tool like that is something that they could turn to help them think things through. Um, so that kind of interpretation, I can imagine longer term observing project where you're observing variable stars, right? So you're seeing changes in brightness. Um, one of my simulations is a Cepheid star property explorer. So if you've gone out and you've observed a Cepheid star and you've figured out, oh, that thing has a period of 10 days, okay, that star is about 3,000 times brighter than the sun because we've got a tool where we can actually just change the period of the Cepheid star and see what the light curve would look like. And so you could have this as a tool that somebody could use to actually interpret their observations. You could make a similar one for like mirrors, or for eclipsing binaries, right? There are so many eclipsing binary simulations. It's kind of funny because there's topics where like somebody makes one and then somebody else comes along and says, I want one of these, and they don't realize that somebody's already made one. And so then we end up with, I think eclipsing binaries is one where we have, yeah, there's like University of Nebraska had one. There's another at New Mexico, another one. Yeah. And, and so, or like Drake equation calculators. There's like 20 of them. And I felt kind of bad when I wrote mine, but I was just like, oh, but I just want it presented this slightly different way. But anyway, well, like with eclipsing binaries, that's an observing project. Go and observe some eclipsing binaries, and then you could fire up a tool to help you actually interpret what you're seeing.
Yeah, I could see where that would be a real good experience out in the field because several of us, we observe through our eyepiece and with our iPad adjacent to that. And so we're looking and reading and learning from the iPad and then observing through the eyepiece.
Mm.
And so to be able to run a simulation of what we're seeing in the eyepiece to match the different parameters that we're observing, I think that would be really, yeah, it'd really be educational.
Well,
Good hands-on.
yeah, and so on that note, I think that there's a few sims that people have done that actually will simulate a view of the sky with different equipment. Um, I'm blanking. I think that there are some in here. And so that's another thing, right? Where you could say, okay, I was looking up here and I'm not quite sure of what I saw. Well, what if is it worth it to drive back home and get the bigger telescope to bring out? To say, well, would doubling my aperture really end up helping enough to distinguish what I think I saw? Or, do I just need to call my friend, up at Lick and be like, hey, take 5 minutes with the, with the nickel and get a shot of this for me.
Very good. And then my last question, you had a slide of your 400 plus a summary slide, and on there was listed, I think it was called sonifications. What
Oh,
are
yeah.
those kind? What are sonifications?
Okay. So this is kind of a branch of visualization where instead of and so instead of well, also in addition to showing things, having sounds that emphasize some particular aspect of what's going on. So these are so. let's see now. This is my favorite. Um,
Star sound or
so,
something?
so there's this site, the Astronomy Sound of the Month, and they have, oh, this is just my favorite. Does my, let's see if my sound comes through. Did that come through? The sound? Nope, you're not reacting to the sound.
Yeah.
So let me,
You can stop sharing and reshare and check the box to share sound.
yeah, let's see now.
I didn't know there was such a thing as astronomy sound of the day or the month. Okay.
Okay, I guess I do have to turn off the share completely. Okay,
Really?
just a second. Now let me hit share again. Oh, where is, oh, there's the checkbox. Okay, there we go. Oh, oh.
We can hear.
And so they've taken this subset of the Hubble Deep Field and where people have measured the redshifts and they've used, a particular cosmological model to relate that redshift to a distance. So you mouse over a galaxy, you get the number displaying of its distance from us, but then the sound is representing the redshift. So a low redshift is high pitch. So that faraway galaxy with its large redshift is this deep tone. And so this gives a way for people to,
That's cool.
now I'm going to turn the sound off. Well, I'm just going to get my cursor off of there so it doesn't keep.
Thank you so much. That's really cool.
That's cool. Yeah.
Yeah, and so this is actually, sonification is it's sort of the looming immediate necessity for the simulation community. And it's a very challenging problem. So because it's a way to make the simulations accessible to anybody.
Yeah.
And so in terms of making these simulations usable, some things are easy. On the interface side, okay, if you're coding things up in JavaScript, HTML, you can use the tab key to move to this controller, move to this controller, move to this controller. You can use the arrow keys to change the numbers. That part's easy. You can have anything that's displaying like a number or displaying text, that'll get picked up by a screen reader. But so much of what's going on in the simulations is this visual representation of situations. So thinking, for example, of the orbits simulation uh, from PhET. Oh, I bet that if I just start typing PhET in my bar, it's going to come. There we go.
Hmm.
So, so the version of this, their first, let me go ahead and I'm going to turn off the sounds for the moment, right? So you start playing around with the orbit simulation. Think about how much information is being conveyed watching this. You have two objects. For each of those objects, you have an X and a Y position, right? So we have two objects. So every variable we're going to be multiplying by two. So you have four pieces of information related to each of these. The mass is being kind of related as well with the size. Okay, the mass, you can easily relate that by just having a number being displayed. Okay, so there's four pieces of information per object here that's being represented in the graphics. That's a very rich thing for people to be thinking about. Oh, wait a minute. That's not everything, right? Because we have this vector showing the velocity. Well, we can turn on a vector to represent the gravitational force, right? So that's an additional two per object. So we got six pieces of information, six variables per object that we can just get visually here. And for somebody who's not for somebody who's not able to just sort of see this, how can they be getting that information out? And so one of the strategies for that is sonification, where you pick one or two highest priority or most informative variables, and you attach a sound to that. So here, I'm going to turn the sound on again. Are y'all hearing that coming through?
Yeah.
Yes.
That tone,
Mhm.
right? And
Yep.
so that tone is representing the district from the barycenter. And but again, what I'm about to do here, I'm clicking on that velocity and I'm changing the velocity, right? That's somebody that right there is something that, you know, that's a non-accessible interaction right there. But it causes a change in the system that's really noticeable. So, you saw how as it flew away, it got quieter, and as it falls back in, it's going to get louder and louder and louder. Okay, so that's conveying some useful information for reasoning about the situation, right? You could have a whole conversation with the physics class about what's going on here.
Hmm.
Now, in this case, so I brought this one up because this is like the way I see it. My take is that this particular simulation is like the gold standard, the best that anybody, well, need to retire that term. Um, this is like the best example I've been able to find of somebody really finding a way to make everything accessible, but it required having an interface that pops up a little display for every relevant variable that can be, that can be adjusted, by typing. And that's, but even then, um, it's still going to be, this is basically, as far as I can tell, this is as good as you can do with this, right? Because what you could do is you could pause, get your X and Y position, hit play, pause, get your X and Y positions, and kind of mentally put that picture together. Um, but this, the amount of work that FET is able to do, like they spend $100,000 per sim, right? They're a multi-million dollar project, right? Because their full development process is just, it's amazing. And
That's great.
that's way beyond the scope of what basically any of the rest of us can do.
Thank you.
That's great. I'm curious, any questions on the Zoom? Ray, Omar, and I don't know who's there on the phone. No? Any more here in the room?
I have a question. What are you using to help code or create your animations? Are you using any AI tools
Thanks.
to help code and especially in the sense of helping to try and with the initiative to maintain them for their longevity, what would you recommend using?
So I know some people have started kind of experimenting with taking existing sims, feeding them into Claude and saying, hey, Claude, add these features.
Mhm.
And I've seen some people experimenting with just using those AI tools to make sims. Um, I haven't done that. Um, I've done some experimenting, right, to use it to assist with a few particular tasks that I found challenging, um, where, or particularly with like translating. Like I know Python a lot better than I know JavaScript. And so code translation, yeah, that's pretty straightforward. Um, so there's not a clear, I don't I don't think that there's a clear picture yet I mean, part of this is that's a set of conversations I've just started having with people in like the past couple of months. Um, the thing I worry about, um, so there's an advantage in terms of speed, probably, you know,
Mhm.
but um, if it decides to use some obscure package, that's potentially opening another, vulnerability path, or things like I did have a student who made some Sims, who was experimenting with making some Sims using Claude, but with using those tools, but like it's easy to forget how much guidance you need to give those things. And
Right.
it will wander off, getting physics really wrong, getting, and 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 it's easy to miss those things. And if it's producing code that's beyond your ability to read, then you're also losing your ability to do that troubleshooting. So
Right.
I tend towards just writing things myself. Um, you know, I've done a lot of just hand coding in HTML and CSS and JavaScript. I've got a CS student right now. So Foothill's just started a web app development certificate. And so the final course in that sequence is to develop a web app for a customer. And so I'm the customer, and there's an ACS student who is writing up who's writing up a pulsar simulation that I am just chomping at the bit for. And the student is bringing professional level skills to it using, um, packages like React and like the industry standard tools for making web apps.
Mhm. Right.
Um, I also have lately, I, the doing the hand coding HTML, CSS, JavaScript. Um, I'm just too slow in that. So actually, I've gone back to my programming roots, right? I learned to program in NetLogo, that language, from my research project as an undergrad. And it now has a tool where you can make your code in the desktop version, go to their browser-based version, and then download it as an HTML as a standalone HTML file. And over the past week, I have been able to make over the past week, I have made I had the link up here, a sequence of 6 Sims. Right? I produce Sims at a rate I've never produced them before to
Mhm.
build up concepts related to the expansion of space and then all the way to understanding the redshifts that we see due to the expansion of space. So, starting off with a sim that's just we've got two galaxies, space is stretching and carrying them apart from each other. And then going on to the next sim where you say, oh, well, let's look at some of the numbers. Okay, I've just added on some graphs. Then the next sim where we say, well, what if we got a bunch of galaxies? So here's us over here on the left. We got a bunch of galaxies over here. What does it look like as space stretches and carries them away from us? Oh, the ones that are further away from us look like they're going faster. Oh, what about the photons that are coming from those galaxies? So they're sending photons our way, and those photons are getting stretched as they are moving through the expanding space. What does that end up looking like? And so you can actually, I mean, I've never, 6 Sims in, 8 days. I've never done
Mhm.
this. So
Yeah.
once NetLogo added that download from their site as a standalone as a standalone sim, oh, phew, I just
Mhm.
huge acceleration for me.
Very good. Thank you.
Great. Hey, Geoff, I can't thank you enough. That was a great presentation, great information. Really appreciate your time tonight. And on behalf of the group here, I just want to thank you again and give Geoff a quick round of applause. So again, I'll see you soon. I know I'll see you down at Foothills in the near future.
Next Wednesday's our next talk.
I know I'm going to try to get there.
Awesome.
It's a haul for me, but
Oh yeah, I know.
I'm going to try to get there. So thank you. We're going to go on to our regular meeting content. You're welcome to listen in or have a good evening and take the rest of the evening.
All right. Well, hey, thanks for having me out. Good talking with y'all. Okay, good
Thank
night.
you. Take care. Bye-bye. Hey, so one thing that I should have done earlier is publicly embarrass Tim, who has a birthday. So, happy birthday, Tim. Just in case, I know you're getting older, you might not remember that you had a birthday. But not only is it Tim's birthday, but he brought the refreshments and Geoff brought a cake. So if anybody wants any cake and refreshments, yeah,
Pat, let me go ahead and on that note, just tell you a little bit about my birthday that I had.
oh
So, yeah, thank you, Jeff. And I'm sure Glenda helped. She probably picked it up, right? So, I'm in familiar company here, so I can tell you how it is to get older.
Please.
Yeah, I barely remember some things, and I realize I'm losing brain cells, daily, and I don't remember the things I used to. It's the universe has that entropy, right?
Yeah.
It's constant chaos and decay, right? Well, it's going on in our brains all the time. So, the reason for that is all this bombardment we have from all the electromagnetic radiation, right? There's all kinds of things in the spectrum that are harmful to us. Give me some examples. What kind of
Cosmic rays.
cosmic rays, right? X-rays, UV rays. Yeah. So I got worried about as I'm getting older, I started to research how to protect myself and from in this urban environment. It is kind of yeah.
I
So
think I see it. I think I see it. It's on his
there was
head.
an MIT study in 2005. These students attached electrodes to their subjects' brains and then bombarded them with all kinds of different spectra. And they found that there was a way to protect from all these different wavelengths coming in. And it's a Faraday cage. Basically, it's, to protect your. And so I've been starting to wear this one. And I wanted to start marketing them to anybody that might be interested in these. And the next version is going to be lead. And it's going to go all the way around the head. So yeah, this is just a prototype to start with. So, but I wanted to tell you all that I'm working on a project. Okay.
if you
Yeah.
really
To make it
want
more
to
marketable, you need a different color aluminum.
What's that?
To make it more marketable, you need different colored aluminum.
Okay, yeah.
I was going to suggest a propeller too.
But thank you all for the
Propellers always look good on hats, right?
I'll give that a try next.
So yeah, if you want to, hey, if you haven't had an opportunity to sign up for the potluck, here's the potluck sign up page. And if anybody is interested in collects back issues of Sky and Telescope, take these. If not, I'm going to figure out where to put them.
Thank you, Pat.
Yeah. So let's see if we go down.
Let me maximize this a little bit.
Sure.
I'm sharing the screen, so I think everybody can see. There's where we are.
Yep. So yeah. So whatever food, and if you don't sign up, just bring something. But just as a reminder, the 23rd, and if you could arrive at 4:30, we're going to eat at 5. And then we will roll into astronomy in the park, and we'll have a good evening, and hopefully, no one gets food poisoning.
Should be good weather this weekend. The
Yeah.
forecast shows good skies.
It's, yeah. But yeah, hopefully the weather holds up. If you go to the next page, I didn't do this. Did anyone give it? Oh, see, Kate, both of you did?
Did too.
Oh,
I did it because I had to
yeah,
highlight the answers.
yeah. So you know what? I was gonna, yeah.
Oh,
Oh,
shit. It wasn't on the list.
Yeah, there is wolf there and there.
I'll tell you, in all sincerity, I looked at this and I'm learning things about my brain. I had trouble processing that. If you put that into a square, I have no problem doing a word
I think
find.
it is harder it not being square.
Yeah, it really. I'll borrow it for the next one. But yeah, I had trouble. I actually had trouble working through that, and either that or maybe I didn't have enough coffee. I don't really remember at the time. So yeah. Yeah. So thank you, actually, Eric, for doing that, because I appreciate the fact that it's in the newsletter and you made me learn something about myself.
Yeah.
Because yeah, in all sincerity, I'm really good with pattern recognition, and that star shape really messed me up. So next slide, New Moon Challenge. So Casey, how come every one of yours has cloud base to it?
It's a bit cloudy. I mean, it's just cloudy all the
Yeah.
time.
But
She's just smoking before she.
It's local cloud.
Okay, I'm not going to carry that one any further, but yeah.
But your resolution is good because you've enlarged that, right? Casey? I mean-
Probably. It was a 600 millimeter lens though. So.
Okay, well, that's why. Okay.
Yeah.
Yeah, the resolution's really sharp. Nice shot.
But yeah, those are actually, those are all really nice. So, and then if you hit the next page,
The next one's May 7th.
oh yeah, May 17th. So, yeah. The target of the month, and Ray, I think Ray, you're still out there. Great job again. Ray grabbed the Spider Nebula. Yeah. I'm in love with that Orion, or I'm sorry, with the Origin camera that he has. And then the May target of the month is the elephant trunk, and this is actually work that Bill already, he's ahead of the game.
This isn't the elephant trunk. This is the veil from.
Oh, the veil, right?
Where did I get?
'Cause
Sorry.
Eric did.
Yeah.
Eric did the elephant's trunk.
Yeah, I grabbed that this weekend.
Did you? Okay. Well, sorry. See, maybe I'm not as good at pattern recognition because I can't read an email and line up the photo with the name anymore.
Yeah.
I don't, yeah.
Get in the lead.
Maybe, yeah. You know what? I think it was the star thing that threw me off, that made me confuse the photos. No, but thank you. And great images coming back from Bill, from Casey, from Ray, from Eric. I love seeing that. And I know we're seeing a lot of them in the chat, what do they call? Yeah.
We have a small group text.
Yeah. But I love seeing those come through, and it shames me because I'm not outside doing that myself. So
Somebody was imaging Berenices, and I bet I'm the only one that could actually see the stars.
Yeah.
Because I was I slept outside on Saturday night, and there it was right overhead.
Well, Eric was at Campo Seco.
Yeah.
You guys had a good night up there?
We did, yeah.
It was clear. And Kabir was there. And he's
Yep.
not here tonight. They came out.
Yep, our newest young member. Yeah, so now we have 4 young people. I don't know who's on the iPhone here. It may be one of them, but it's great to have the young members coming in. But Eric, if you take us to the next slide, I think Jerry, you shared this with us. But just a note from Becky Greider. I don't know Becky. Yeah. So, and I wanted to share this because it's a note from Becky saying that, well, she hasn't been here in a long time. She, still thinks of us, and she has some equipment that she is interested in handing off.
It
And
was a club scope to begin with, and it was not one of the better ones. I think it was one of those closer.
No, she had a 10-inch on a German control.
Oh,
Because she had me put it into a Dobsonian mount.
oh, okay.
And I did, but when I did, I put the focuser off to the side, so she brought it back to me to rotate it in the tube. But I had it in the thing too tight, I couldn't rotate it, so whoever gets it needs to loosen it up and rotate it so the eyepiece is at a 45-degree. But it's a Meade 10-inch.
okay, and yeah, I don't know. I wanted to share this. I don't think we've gone back to Becky at all to, address this or follow up. So I don't know. In fact, we should figure out. I don't want to leave her hanging
How
either.
fast a scope is it? Jeff?
4.5.
Do we want to take it back in as a club scope at this point?
It
Is
was
it?
meant.
Oh, it wasn't.
It was
Oh,
scope.
oh, okay.
She just took it off a German mount, put it on
Okay.
a dog mount. But
Do you know if she is asking money for it?
No, Jerry, I don't know. Do you remember? Yeah. Okay. Was she asking for payment or was she?
She didn't seem to be.
Yeah.
It's not clear from there, she's just looking for a good home for her.
Is it-
Like I said, I
I
forgot what my
Okay.
customer was.
Yeah. Okay. So, yep. So Doug will reach out. And then the next one, I was hoping Jinka was going to be here tonight too.
He emailed, texted me, he's got another thing he had to go.
Oh, okay. So yeah, so you can see there, he shared with us that he was accepted to the summer internship at Chabot Space Center. And I went online to understand a little bit more about the program, but what he'll be doing is actually doing presentations and walking guests through information at Chabot. So if you want to find Jinka, I think he's going to be there.
We should all show up as a
We should
big
do
group.
Yeah. Yeah.
That's what Mark Gibbons did when he was young. He worked at Chabot
Oh,
doing, he was like the astronomer's assistant.
So did Tom Hanks.
Tom Hanks, the actor?
Yeah.
Is that right? Wow.
So did Fetching.
During Apollo 13. He actually helped track Apollo 13 by eye. When it was going on.
oh, wow.
We actually had a speaker
Uh-huh.
come in and talk to us.
Yeah.
It's probably online
One of the
in
reasons
our YouTube archive.
Tom Hanks pleaded with Spielberg that I gotta be in that movie. I gotta be in that movie because I was part of it when I was a kid.
Wow.
Cool.
And Tom Hanks grew up in Sacramento. So yeah.
I think it was Eric and me and Mike and Lonnie and Bill went over to Chabot for their ATM workshop.
Yeah.
And it's a little different, but they're very productive. They put out a lot of scopes.
So we got a special tour we got. Anyway.
That's right, we're gonna look at it.
A million kids there that night, remember they all camping out there in the pajamas?
Yeah. They were camping overnight, yeah.
Sometimes it's good to be tired.
Huh?
I built a lot of Kermit over there.
Oh, yeah.
Of course, it was a lot closer when I lived in Tracy,
Yeah,
and the traffic was never as bad.
it sucks now.
Yeah.
Yeah, but I really do think that we need to do find out when he's working and bomb him.
Sure. I'm open to
Says he
that.
has to do a minimum of 8 hours each month. I expected.
Actually, he didn't tell us that. I pulled this off their website, but I wonder if he knows what he signed up for.
A minimum of 2 4 shifts per month. So.
Yeah,
Right, doesn't have a license yet, so.
yeah. If you go to the next slide, little outreach. So we did some work at Villalova School, at Cole School, the Earth Day astronomy Earth Day in Victory Park. Vader showed up.
The center one, Pat was helping this guy find the Death Star.
Yeah, yeah.
The daytime.
And then we got washed out for astronomy in the park. But I'm terrible at taking pictures. So Casey, I appreciate it when anybody takes a picture at any of these events. I did take the one of Darth Vader because we had a bit of a conversation that he tried to squeeze my throat. And it didn't work, but yeah, with his mind. But something struck me as I was looking at the pictures and everything. So if you go to the next slide, something caught my eye. Do you see anything in that picture that really catches your eye?
He's not looking through the scope.
Doug being lazy.
This is my version of the star word find thing. So if you go to the next slide, here's what really, in all honesty, I looked at that picture. Go to the next slide. Rodin's the thinker. I saw this in the picture, and I was inspired. I was truly inspired by our thinker because I look at it and I thought, that's the thinker. So I hope the EC doesn't mind, but if you go to the next page,
Thank goodness he's wearing.
I had an artwork commissioned. So when if Doug's not available for anything, in homage to his Douglasness, we'll take this statue with us and we'll put it out there. It's concrete. I need your truck to move it.
He says it's so he does.
I confused pictures that people gave me. Yeah. But yeah, so Doug just,
Good work, man.
wanted to keep you in mind.
Yeah.
So yeah, if we move off of the naked Doug, this is actually
Set it up.
this is actually one of Casey's pictures, and I grabbed this at the beginning of the month because I like taking one of them and using them as a backdrop for a slide. So I don't remember where I found this, Casey, but this is yours. I hope that's yours.
Yeah.
I think it's yours. I think it's yours. Yeah.
I think it was a newsletter.
Yeah. So if you go to the next slide there, I just use that as the backdrop. But
How much immigration was it? How many?
What? You mean how long did it take?
How long? Yeah.
It took me 7 hours because it was the first time I used Fix Insight for my.
No, the exposure.
I think we imaged it instead of Orion, right? So I think it was only like an hour.
It was less than an hour, but
Yeah.
I didn't get to use it.
Oh, okay. Because your stars are real tight. They're not footballs. So
It was less than, it was like 48 minutes or.
yeah, the track is
Something like
good.
that, yeah.
yeah. So Saturday night HASP, Eric and Casey may be going. I'm going to go up as long as the weather is good. I don't know if anybody else is interested in heading up, but at least we'll keep everybody informed.
My wife's birthday, I can't go, I'm dying.
She doesn't want. She doesn't want to go up there?
It's her birthday, the last thing she's gonna wanna go is Golden Mountain.
Are you thinking the heliport or Peddler?
I don't know.
Pedlar's clear.
We were thinking of Heather, actually.
Yeah.
Heather, to be clear, I don't know if there's any, trees down though.
Yeah.
None of us. Maggie and I just came back 88
Oh, did you?
last weekend, and so it looked, there should be fine. But like I said, the Lexus is a little on the low side, and so I didn't bother going up that direction.
It's the thought that counts. At
Is
least
that-
it's the thought that counts. At least you went past it and said it's clear. So, yeah. But yep, coming up on New Moon Challenge, May 23rd, potluck. We'll go have fun. And then you see June there for the 6th. June 11th. June 11th, we're in this room again for the meeting. For July, we are most likely going to be in a room in the building next door. So we'll make sure we get it note out to everybody for that. We have a room over that's actually the Teachers College. And I think we did a quick electronics test. The room worked. Yeah, everything worked. And it has a little less echo than this room too. So it may be a better solution in the near term. And yes, it's $25. It's $25 for 5 to 9 p.m. They book it as a 4-hour block. We actually, we haven't committed yet. I want to get clearance from the EC that we're still good with that. But the room is available through the end of December, and we could book it into next year if we chose to. My thought behind it is if we at least book through the end of December, we'll know what's going on here. We'll be able to see what's going on with the construction. And frankly, we have this room booked through the end of December, but it isn't clear when the construction will begin in this building. And my fear is if we lose power or internet in this building because of something that's going on, then we've got a different problem. So I think we need to get out of this location anyway.
We have Pat book that room tomorrow morning until end of December. Anyone else want to second it? Second.
I'll make an amendment to that. Because there's another larger room upstairs that it'd probably be more beneficial for doing the annual dinner. So might see if you can't also book that for January.
Okay. And just that location for the dinner, it's actually a very nice spot. It's $30 for a 5-hour block. So it's, yeah. Okay, so amended, yeah. Do I have a second on the amendment? Yeah, thank you.
Does it be contingent on this building being worked on? I mean, if they're working in here, will that be infected?
No, in fact, because it's the building next door, and it's actually a very nice building. But it's the building next door and there's no construction planned there.
We're talking about the dinner was up here.
No, it's over in that building as well. Yeah. Yeah, it's the second floor on that building. But yeah, there's so many questions and in all sincerity, I can't get any answers about this building. So all in favor of aye?
That's good that we have to vote on it.
Yeah. Okay,
We just
and
voted.
Pat, the June speakers in person?
I believe so.
Omar, yes, is the June speaker in person?
I'm trying to unmute. Can you hear me?
Yep,
Yes.
we can.
Okay, yes, I was gonna try to get in before the end of the meeting. If you can invite a friend, and we'd like to fill up the room because we do have a live speaker, and it's gonna be a fun talk. So she'll be coming down from Sacramento and talking about her analog mission, which was simulating 2 weeks living on the moon. And so, yeah, we got a live one.
Are we going to go to dinner before?
Yes, I think so. I haven't decided exactly where that's happening yet, but I'll keep you posted.
Thanks, Omar.
Yeah, no problem.
And not that it matters, I won't be here next month, but Doug is going to run the meeting. So the end of June there, and then just watch the form for, going up the hill. Next slide. Oh, Geoff wanted to talk again so I improved it actually. It's much clearer. I improved your spaceship.
At least you have clothes on.
So, so if you look at this, it's now a word from Geoff because he asked for some time. But these are pictures that he gave me sometime back in the early 90s, and I had them on my computer at home from the old website. But if you look, this was not mine. This was his. Having completed his work on how to serve humans and their pets, Geoff decided to return to his home planet. I'm just asking, what do we really know about Geoff? Because do you recognize this? Okay. So it's a Twilight Zone episode called To Serve Man. And that's a cookbook. Exactly. So, Geoff, I will retire these pictures.
You keep.
No. Okay. Geoff, I'm going to have a statue made of you in your spaceship, and we'll put it out with Doug. But
Little flag sauce.
At least but you asked for some time, so you have time.
Thank you.
I have the camera pointing right at you.
Well, I'm gonna come over here because I'm gonna have Pat hold this.
Oh, okay.
Thank you. Okay, Pat is the mirror box.
Yeah.
And it goes in the mirror box like that. This is the cell I've been working on for my meniscus. And so this is 18-point flotation cell, sort of designed around the JB Astrocraft. And this is the puck that's going to be glued to the center of the mirror. So the mirror is going to go right here. When it's looking up the sky, it all sits on the 18 points. When it's looking down the horizon, all its transverse weight is on the puck. So I'm going to use this in the scope and I'm going to test the mirror in it. So what I'm going to make this next week is I'm going to make a thing that sets it about an angle like that on the floor. So I'll test it on the floor at this angle. And then when I take it out to hardware test it on the star, it'll be at the same angle, only this is in the scope. Anyway, I have taught myself how to powder coat, and so this is all powder coating. It's not done very well because I'm an early powder coater. So if you look at this, there's some glitches on it. I'm actually kind of thrilled about how this is turning out. All right.
And the color is?
I was gonna go for carrot. And the closest thing I could get to carrot was Chevy engine orange. But it's a powder coat. I'm doing it in my kiln, my sloping kiln. And that's it. Couple differences will happen. I'm gonna have a different spraying load and adjustment for the collimators. I'll have some screws put in for putting it in the box. That's it.
How do you adhere that little central puck to
Say
it?
that again?
How do you actually adhere the central puck?
This is a puck, and it's gonna be our aquarium RTV glued to the back of the mirror.
Oh, okay.
So when the mirror's looking up the sky, all the way sits on the 18 points. When the scope comes down like this, instead of having whistles on the side of the scope at the center of gravity, it has no center of gravity because it's a meniscus. So it's gonna be glued to the center of the mirror, so all the weight will be right on the center.
Right.
And it's about that big, and so I'm predicting it'll distort the mirror about that big, and the secondary mirror is that big, so fingers crossed it won't mess anything up.
What was the diameter of the mirror?
20-inch F3.
20-inch F3, okay.
And it's about that thick. It'll be a miracle if all this works.
Are you
I'm
gonna,
actually optimistic about it. Thank you.
are you gonna luminize it or silver it?
Silver.
Silver.
Nothing but silver from now on.
Cool.
So Jeff, my promise to you is I will retire these pictures because I got plenty of other stuff you gave me.
Yeah.
Uh,
Picture of him with the spaceship looks like invaders from Mars.
Yeah.
I'm gonna take a picture of that because, UFO made to my friend when I was a kid, looks just like that, and I want my sister to get a look at that, so. So, right your legs and the rest of your body.
They've been.
Actually, I wasn't wearing a shirt when that picture was taken, he put the shirt on me, cause I'm so gross.
No, yeah,
Everybody's been taking clothes off.
yeah. No,
You're just
I-
for the movie Attack of Mars, was it? Mars Attacks, which is just the head. That's what it reminds me of.
You know what though? The really cool thing is with AI, you can make yourself look better. Because I don't think you look this. I know.
We don't want to see the images on your
I know.
machine.
No, but I'll tell you the truth. One of the coolest things that I stumbled into was I have hundreds and hundreds and hundreds of black and white photos that were my mom took of us as kids and going back. If you take those black and white photos and you drop them into Gemini AI and you say, colorize this, it does a beautiful job in adding color to a photo that never had color. You can tell it what some of the base colors are. If there's a car, you want it to be red, you can tell it that, and it gives you something back. And I surprised my mom with some photos that were from 1961 that were old black and white snapshots that I had it color. I had them I had AI colorize them and upscale them so I could print them on 8x10 on a metal print. So yeah, Jeff, you won't see these again. I have no idea what's next. Oh, you know what? Yeah. Ray and Bill's supernova work. So yeah, I just think that's really cool. I love the fact that, we have, some really neat pictures showing up on, from the group. So congratulations again, Ray and Bill, when you see him. And I think, that's thanks for joining. Remember, the sky is for everyone. Next month we have Domina Stamus. That is going to be really interesting. I'm going to try to call in for it, but yeah, the sky is for everyone, including Abe Lincoln and C-3PO. So that's the end of tonight, unless anyone else has anything they want to share. No? Okay.
There's more refreshments. Help yourself.
Yep. Thank you, Ray and other person. Thank you very much. Have a good evening. And we'll talk to you next month, and gavel, end of meeting.
Where's that sign up sheet?